What we want to demonstrate today is how to know whether a given quadratic expression is a perfect square or not a perfect square. But before we can swing into solving these problems to determine whether they are perfect or non-perfect squares, it is important for us to know first of all what a perfect square simply means. Now you know what a square number is, right? For example, when you solve a problem and you end up with an answer 4, you know that 4 is a perfect square because 4 is made up of 2 and 2, or written as 2 squared. 4 is a perfect square then. So, bringing it to our knowledge of quadratic expressions, determining what a perfect square expression is also very important. Remember that in our last class, when we discussed quadratic expressions, we showed that when a quadratic expression is factorized, it usually ends up with two answers in two different brackets. Like this. When you solve a quadratic expression, you might end up with answers such as x plus a in one bracket and in another bracket x plus b. Let's use this as an example. Looking at this, you notice that what we have in both brackets are not the same. So we can easily say that this is not going to be a perfect square. In fact, it is not a perfect square expression. But what if we end up with an answer such as x plus a in one bracket and x plus a in the other bracket? Do you know that we can actually write this as x plus a in a bracket and put a square to it? Because both brackets have exactly the same expressions. So it means that perfect squares appear this way. So this should form the basis of what we are going to do today in trying to determine which of the expressions on the board is or not a perfect square. To take it a little further, using the example I just demonstrated on the board, x plus a squared, close the bracket squared. If I open up this bracket, I'm going to end up with an expression of this nature. X squared add 2ax add a squared, where x squared is standing in our place of the usual x squared we have in the general quadratic form, which is ax squared plus bx plus c. So comparing the expression of the perfect square which we have right here on the board to the general quadratic form, you notice that the x squared is the same x squared we have here, but the value of a this time around is unity, that's 1. Then for the case of bx, in the place of b, we have 2a. And then in the place of c, we have a squared. What does this mean? What it implies is that when we solve problems having to do with a perfect square, or when we want to test for perfect square, it simply implies that the middle term, the test for perfect square, implies that the middle term is a multiplication of the number 2 and then the term that make up the square on the c part, along with the coefficient of the x squared as well. So if it's the coefficient of x squared here was, let's say, c, here will be 2ac, then x. Take that in mind, because when I begin to solve these examples, I am going to use this to demonstrate it. Let's swing into action immediately and see whether any of the expressions here is or is not a perfect square. Remember this, because this is the main test of a perfect square by analysis. Let's do it. Using the first example we have on the board, we want to see whether the expression x squared plus 8x plus 16 is a perfect square. Looking at this part, this can be rewritten as 1x squared, isn't it? Or 1x squared. For this part, we are going to demonstrate to see if it really fulfills the rule of 2 multiply the coefficient of x squared and multiply c. We will see if that will demonstrate exactly what it is, if that will give us the answer we are looking for the test of a perfect square. But look at 16. The number 16 can also be written as 4 squared. So what this implies is that the x squared term and the c already fulfills the perfect square rule. But what about the middle term? In the first demonstration I gave to you, for an expression to be a perfect square, it has to meet up with 2, multiply the coefficient of x here, which is 1, then multiply c, which is 4. This, which we have here, must be able to give us the value of the middle term. So let's check. If this gives us the value of the middle term, then it means that this expression is a perfect square. Let's see. 2 multiply 1 is 2, multiply 4 is 8. This is the x, the coefficient. If I bring it down, notice that this 8x is also the same thing as this 8x. By this, it proves that the expression 8x plus x squared plus 16 is a perfect square. This is how you know. Let's test it again on the second example. The second example we are given here on the board is y squared plus 5yz plus 81z squared. Y squared plus 5yz plus 81z squared. Let's see if this is a perfect square. First, y with a square has a coefficient of 1, so we can rewrite it as 1y, all of them squared. Plus, I'm coming back to this, but let's look at this side. Is this a squared number? Yes. We can write it as 9z all squared. This will give us 81. So it means that our first term and our last term has already proved the perfect square analysis. But without the middle term, we can't say that this is a perfect square. Therefore, let's test. For the middle term to stand up as a perfect square, it simply means that it must prove that 2 multiply the coefficient of y, which is 1, multiply the coefficient of z, which is 9, must be able to give us the number 5. So let's see, does it give us the number 5? 2 times 1 is 2. 2 times 9 is 18. 18 is not the same thing as 5. By this, we say that this expression is not a perfect square. So first, this is a perfect square. The second one is not a perfect square because the middle term does not agree with the analysis of a perfect square. Let's try the third one to see also if that one will be a perfect square. The third example we have here is x squared upon 4 is a fraction minus 3x add 9. We can rewrite this to demonstrate the squared terms that we showed in the rule of testing perfect square. By rewriting this as x upon 2 all squared with the coefficient of x being half, yeah? Minus, leave this, let's write down our plus. 9 can be written as 3 squared. The first term and the last term have already proved the rule of perfect square. But we are going to check the middle term to see if it really proves it. So the middle term works with 2 times the coefficient of x is half and c, which we have here, is 3. Okay, with what we have here, 2 multiplying half gives us 1, 1 multiply 3 gives us 3. So the 3 here is also the same thing as the 3 here. Actually, it's negative, okay? So negative 3 is the same thing as negative 3, meaning that the whole expression proves true to be a perfect square. So we say that expression number 3 is a perfect square because the rule proves true to it. What about expression number 4? Expression number 4 is 4t squared. 4t squared minus 6tu plus 4u squared. Merely looking at this side, we can rewrite 4t squared as 2t, close the bracket square, minus, we are coming to this, let us demonstrate if the last term shows a perfect square. This can be written as 2u, close the bracket square. So the first term and the last term proves true to the analytical test of perfect square. But what about the middle term? Let's see. Can this prove true? 2 times 2 times 2. What does this show? 2 times 2 times 2 gives us the answer 8. 8 is not the same thing as 6, which we have up here. So this is not a perfect square. Do you see how to test that? It's not difficult, isn't it? Let's see a little further for the next example. The next example we have here is 4a squared. 4a squared plus 12ab plus 9b squared. The test for perfect square is easy. For 4a squared, this can be rewritten as 2a, close the bracket, squared, plus, we're coming back to this, let's know what the c term will be first. So the c term is going to be 3b close the bracket, or squared. So does the middle term appear the same to be 2 times the coefficient of A, which is 2, times the coefficient of B, which is 3? Will this give us the number 12? Let's see. 2 times 2 is 4. 4 times 3 is also 12. So this 12 is the same thing as this 12 up here. What this implies is that this expression 4a squared plus 12ab plus 9b squared is a perfect square, because all the terms of the expression prove true to the analytical test of a perfect square. Last example is on the board, which is 9b squared plus 16c squared minus 24bc. 9b squared plus 16c squared minus 24bc. Before you jump into solving, it is important to rearrange the problem in the form of ax squared plus bx plus c. Don't forget that. So the first one, 9b squared, is already properly arranged, but this is the c term, which doesn't have to stay here. Hence, negative 24bc comes next, y plus 16c squared comes third. Now we can try to test out whether it is a perfect square or not. For the first term, which is 9b squared, can be rewritten as 3b, close the bracket, squared. For the second term, we just give a little space and wait, because we need to find out what the c term will be before coming to check it out at the middle. So 16c squared can also be written as 4c in a bracket squared. And so for the middle term, it's going to be 2 times the first term, which is a, where we have 3, times the second term, which is 4. Will this value we have here be equal to 24? If it is, then this is a perfect square. Let's see. 2 times 3 is 6. 6 times 4 is 24. So 24 is equal to 24 that we have up there. It means that this expression in question number 6, 9b squared plus 16c squared minus 24bc, is a perfect square. This is how you run analysis of an expression to see whether it is or it is not a perfect square. I'm going to show you another method of solving or checking whether an expression is a perfect square. But for now, try practicing on this method of finding out whether an expression is or is not a perfect square. Then, before going over to the next method, which is the discriminant formula method. See you then.